All right. Hi, everyone. So we'll get started here. A few reminder items over here listed here. So next homework is due Tuesday and almost midnight, 11:55. Now the last homework will be due on Monday. Okay, so it's Monday on the finals week at 12:50. Okay, so I put this one a little bit earlier so that you guys can get the solutions for study, okay? Because we'll have final exam on the next day, on the Tuesday, which is being scheduled by the university at 10 to 11:50, okay? So I'll probably send you guys the final exams again in email a little bit earlier than 10 o'clock, okay? I have set the final exam assignment on the Moodle. You can turn it by 12:30, okay? So I have a little bit extension in time there. So you can have some extra time, okay? But if you have difficulty in like turning it on time, just say if you need 10 or 15, 20 minutes, let me know. You can still turn it in, okay, in that way. All right. So first, I would like to congratulate you guys on exam 3. Most of you guys on that. Okay, so you guys did really well. The average of the class was about 85%. Okay, so that's really good. Okay, so I actually left the comment with your grades on exam 3 on Moodle, so you can see what's your current grade it is. Okay, if you submit your exam on Moodle. So there's just one of you had difficulty submitting on Moodle, but the rest of you guys all have submit your exam 3 on Moodle successfully. So you got the your current grade, okay, in the comment. All right. Any questions you guys have for the upcoming schedule here, the plans?
For homework 11, are the questions available on Moodle already?
No, not yet, but it should be sometime on Monday or Tuesday. It should be available. Okay.
Okay, thank you.
All right. All right. So as you can see, we have only 2 assignments towards the end of semester. So then the finals will be similar to these 2 assignments. Okay, the problems in these 2 assignments. Okay. All right. So let's get started on the lecture part today. So today we'll be looking at section 17, chapter 17, section 4. All right, we'll be looking at the equation of motions. This time we'll have rotation about a fixed axis. Okay, so the last time we are pretty much focused on the uh, equation of motion, but on not having rotational motion in that case. Okay, so again, we'll be doing a reading quiz first, and then a little bit on lectures, and then we'll be looking at concept quizzes and attention quizzes, and then a couple examples, and then if we have time, we can have some group problem solving. Okay, so the first is the reading quiz. So go ahead and try this too. Send me your answers in the privately in the chat. So again, this will be credited as extra credit. Okay. So go ahead and do that. All right, so everyone has sent your responses to me already. So let's take a look here. The first one here says in a rotational motion, the normal component of oscillation and the body's center of gravity is always. Um, so the normal component of oscillation should be pointing towards the center of rotation, okay? And then this is about the center of gravity, so it should be directed from the center of gravity towards the center of rotation. So on the first one, it should be C, okay? That's the first one. And the second one, it says if a rigid body rotates about point O, the sum of moments of the external forces acting on the body about point O equals to which of the following? Okay, so we are looking for the sum of moments of all the forces about the x rotation going through point O. So then this guy we should be using I sub O, the moment of inertia about point O, okay, times alpha. So that should be B here. Okay, so C and B for these two. Okay. All right. Now let's look at the lecture part of the today. It's pretty easy. So this is just about the equation of motion. So the last time we mentioned about three equation of motions. So the first one should be the net force in. If you use x, y coordinate system, then it's net force in x. It should be equal to mass times the acceleration in x. And then net force in y should be equal to the mass times acceleration in y, okay? In this case, if we have rotational motion, if the rigid body is rotating with a certain point O, or the axis through that certain point O, then the most convenient way to set it up is to choose a normal and tangential coordinate system, okay? So NT coordinates. In this case, then we'll be looking at the tangential component of the net force. So summation of force in the t direction, that should be equal to mass times acceleration in the tangential direction, okay? And then for the normal direction, summation of net force in the normal direction then should be equal to the mass times the acceleration in the normal direction, okay? But for a rotational motion, the acceleration in the tangential direction, okay, so this is about the center of mass g, it should be r of g times alpha, okay? R sub g should be the distance from the center of gravity to the axis rotation, okay? And then alpha should be the rotational angular acceleration. And then for a normal component, the acceleration should be equal to the r times omega square, okay? So this is the content we learned earlier in the class when we are having rotational motion, okay? You can, if you don't remember it, you can go back there and then have a quick review on that, okay? Now, if we have the equation of motion, so these are the three equation of motion we'll be looking at, okay? So the first one, again, is the net force in the normal direction should be equal to mass times acceleration in the normal direction, which is equal to mrg omega square, okay? Omega is the angular velocity. In the tangential direction is mass times acceleration in the tangential direction, which is mrg alpha, okay? Now, because the object is having rotational motion, so the summation of moments, okay, from the external forces, okay, and then the moments given, if there's any, it shouldn't be zero because this time you are having rotational acceleration, okay, if there's acceleration, rotational acceleration, okay, it should be equal to moment of inertia about this particular x rotation going through this point O times the alpha, the angular acceleration. Okay, so now this case, this is not equal to zero. Okay, now for I sub O, we can always use parallel axis theorem on the top here, on the top line, top paragraph over here. So I sub O can be calculated if we know I sub G, x moment of inertia about the rotational axis going through the center of gravity, okay, plus m times rg square, okay, so this is the rg is the distance from the center of gravity towards the axis rotation about O, okay. So that's the guy over there. So then these are the three equations we'll be looking at today, and then we'll be using these three equations to solve the problem, okay? So the procedures for analysis, okay? So of course, first you want to establish the coordinate system, okay? So most conveniently, if there's a rotational motion, we take normal and tangential direction, okay? And then we'll be drawing the free body diagrams indicating all the external forces, and then if there's any moment couples on the body, okay? Then we can calculate the maximum moment of inertia either through IG or through IO, okay? And then write the three equations of motions, identify the unknowns, and then solve for the unknowns, okay? So because we only have three equations of motion, so the most quantities of unknowns should be just up to 3, okay? We can only solve for 3, okay? All right. And then if there's more than 3 unknowns, you probably will have to use kinematics to solve for the additional unknowns, okay? So we'll take a look on the first concept quiz here, or actually there are 2 of them here. I'll set up a breakout rooms for you guys to work on this together, okay? So I'm going to again create let me just create 3 rows because we have 9 of you guys, so then each of them will have 3 of you in the room, okay? So 3 rows automatically assign participants, okay? I'm going to have it created, okay? Now the rows are open, you guys can join the rows, okay? All right, so you guys are back, and some of you guys have submitted your responses to me. I think I had each at least one person from each room has submitted the response to me. Okay, so we can take a look here. So together, so on this one, the first one we are looking for the magnitude of the angular oscillation. Okay, so if we are looking for the oscillation, angular oscillation, then if you look at the three equation of motions, you'll probably figure that we should look at the last one on the moment, summation of the moment about it should be equal to the mass moment of initial times angular oscillation. Okay, so the angular oscillation appears in this equation here. So then alpha, it should be just equal to the summation of moment of initial divided by the moment, summation of moments divided by a moment of initial. Okay, so moment of initial about O at point O, x is going through O, this should be fixed. So then we are really looking for when we get the maximum for the moments. Okay, now for this rod here to be having rotating with this end, if we pick any particular point here, say with angle theta here, okay, so the center of gravity should be at the point, center point over here. Okay, so that's this mg here, or w. So then this is the force that have moments that's not at zero, okay, about the o-axis. Okay, so that's the only moment we'll be considering here. So then we will be doing mg times the length of this guy, or half of this guy, half of length here, right? Half L. So summation of moment about O should be mg 1/2 L, right? Then we will take the cosine of the angle theta, right? Because moment initial, the moments, if we are on the torque, for the magnitude should be the force times the distance times cosine, okay, of sine of the angle the two makes. But in this case, we are given that angle, okay, so then it will be cosine of the angle, right? So then when do we have maximum moments from this expression here? These are fixed, fixed, fixed. So then only when the angle theta changes. Okay, for cosine theta, when theta is equal to 0, then you have maximum, right? But on the other hand, when theta is equal to 180, you get minus 1. Okay, that's also a maximum. Okay, so this one then would be D when the angle is either equals to 0 or 180. Okay, so then you have maximum the magnitude of angular oscillation. Okay, all right, so this is this guy here. Any questions you guys might have? Okay, just unmute yourself and then ask. On the second problem here, it says in the same problem, when the angle theta is equal to 90, the horizontal component of reaction at pin O is how much? Okay, so we can take a look here. If we are at this particular point over here, so the rod is probably going to be moving in that direction. Okay, and then has angular velocity in that direction as well. Okay, so if this is the case, we can look at the free body diagram on this guy. Okay, we should have a weight over here. We should probably have the supporting force from here at O point. Okay, so then in this case, all right, because we are going in this direction, all right, so at this point, the mg, the torque by mg are moments to the rod, because this guy now is going through the O center. Okay, so the moment at this point is going to be 0. All right, so then that will tell you the alpha is going to be 0. Angular oscillation is going to be 0. Okay, if angular oscillation is going to be 0, then net force in the this tangential direction is equal to m times the r times alpha, right? So if that's 0, then this is 0. Okay, so tangential direction is the horizontal direction. So in the horizontal direction, it should be just a force like by this contact point. So this guy can be in this direction and then either in this way or in that way. So that's the force at point O. Okay, so O in the perpendicular direction or in the parallel direction to the normal. Okay, horizontal direction. So then your horizontal direction, it should be 0. Okay, or OH. Let's do it that way. OH, OV, or vertical. Okay, so horizontal direction, this guy should be 0. So your answer on this one should be A. Okay, and then I think most of you guys got this one right. Okay, so but if you still have doubts, just let me know. Okay, all right. Now we'll take a look on a couple examples here. All right, so the first one is having this one having a rod. Okay, so it's not quite horizontal here, but we'll just assume it's horizontal. Okay, let's imagine this is a 3D figure, so it doesn't quite look like horizontal, but it indicates this is a horizontal position here. The rod has a mass of 20 kilogram and then it's rotating at 5 radians per second at this instant shown. Now there's a moment of 60 newtons times meters applied to the rod. Okay, so there's also an external moment there. Okay, in addition to the torque by the weight. Okay, so we'll be thinking about both the moment and then the torque by the weight here. It's asking us to find the angular acceleration alpha and then the reaction at point O when the rod is in the horizontal position. Okay, so the plan here is so given the mass center moves in a circular radius of 1.5 meters. Okay, so the center of mass would be at the middle here. It's looks like appears to be a homogeneous rod here. Okay, so then we can look at the acceleration in the normal component and tangential component. Okay, and then we can also apply the summation of moments to be equal to the I times alpha. Okay, so we'll follow the procedures here. So first, looking at the free body diagram, there's the weight on the rod. There will be a tangential force on the rod at the O point, and then there will be a normal direction force on the O here. Okay, so these are the three forces. Now the rod is going to be, there's an external moment here added on the system of 60 newtons times meter, this guy here. Okay, so forces and then the moments. Okay, external moments. Now this is a connected diagram, so you should have a net force of the acceleration, net acceleration over there, so that can be related to net force m times the acceleration in the normal direction, m times the acceleration in the tangential direction here, and then also the moment. Okay, summation of the moments equals to the moment of initial times angular acceleration. Okay, this is from rotational. All right. So let's look at the two net force equations. Net force in the normal direction, it should be equal to mrg omega square. Okay, that's normal direction. It's the centripetal force basically. Okay, so it's mr omega square. All right, we are given the omega, we are given r, we are given the mass. Okay, so then this can be calculated. So action at point O in the normal direction is 750. Summation of ft should be equal to m times at, which is mr alpha. Okay, now there are two forces in the tangential direction. So this guy is pointing upward, this is pointing downward. Okay, so for the tangential direction, this is going, the positive direction is pointing downward. Okay, so for O, then it's negative. Okay, and then mg is positive. Okay, that should equal to m times r times alpha. Okay, so we have two unknowns over here with this equation. All right, the first equation doesn't have any unknowns. Okay, so then we'll have two unknowns in the second equation. So then we would need a third equation. Okay, So the third equation then will be coming from the net moment equal to moment of inertia times angular acceleration. Okay, so there are two moments. Okay, one is this external moment of 60 newtons times meter. A second moment should be the torque by the weight on the rod. Okay, so the mg, m times g times r, that gives you the torque. Okay, so they are both in the same direction. Okay, they will both make the rod rotate in the clockwise direction. Okay, if we pick that to be positive direction, then we just use the positive sign. Okay, should be equal to IO, which is equal to IG times MRG square. Okay, this is based on parallel axis theorem. For the moment of inertia about O axis should be equal to moment of inertia about G and plus MD square. D is the RG. Okay, so for a rod, homogeneous uniform rod, IG moment of inertia about its center of, or the center point, center of gravity here should be at the center point. It's equal to 1/12 of m, the length of the rod square. Okay, and then this RG is equal to half of the whole length. So then we can use we can plug in those into this expression there. Okay, so this is the IO. Okay, this is the 12, this guy, like 1/12 or 12th of this ml square, plus you would have 0.5, which is 1/2. If you square, that gives you 1/4, okay, ml square. Okay, so then, or if you know that for a rod, homogeneous rod, to be rotated about one end is just 1/3 of ml square. You can just use that one, okay, if you know that. All right. So then substituting the numbers into the this expression, you get 60. Okay, again, this right part over here, plus 20. Okay, it's 20. It's the m. L is equal to 3/3 times alpha. Okay, so then from this equation, you can solve for your alpha. All right, so you have your alpha, then take alpha in the equation in the previous slide, where you have both OT and alpha as unknown in that equation. If you do the substitution of alpha back into the equation, you can solve for your OT. Okay, so then you got your OT to be 19 newtons, alpha to be 5.9 radians per second squared. Okay. Do you guys have any questions on this one? All right. So if not, then we will take a look on a second example here. So the second example here gives you, again, a rod here. So uniform rod, the mass is 15 kilogram. The mass center is at point G, not showing up here, but should be somewhere here about midway on the rod, okay, somewhere. The reaction, you want to find the reaction at point O here, and then the angular acceleration of the rod just after this cord is cut. Okay, so if you cut this rod, this cord here, then this guy will rotate. Okay. Oh yeah, the point G is indicated now. So, all right. So if this is cut, we can imagine then the center of the gravity will be rotating. Okay, in that way, and then the distance from G and O, we can figure that out because the whole rod is 0.6 plus 0.3, which is 0.9. Then from one end to the center of gravity should be half of 0.9, which is 0.45. So then from G to O, that should be 0.45 minus 0.3 would be 0.15. Okay, so that's that distance from G to O. Okay, radius of 0.15 meters. All right, so we'll again apply the procedures for analysis. So first we'll set up an NT coordinate system. Okay, so in this case, N is going to be, so N goes from G towards the X rotation in this direction. And then this is the T direction, or actually the T direction should be going downward. We can take that as positive T. Okay. So we can draw the free body diagram on the right here. There will be this weight, okay, then there will be reaction forces in the tangential direction, in the normal direction. Now this is in the negative tangential direction, okay. The kinetic diagram we could have is the mass times acceleration in the OT direction, in the normal direction, mass times acceleration in the tangential direction, okay. And then summation of moments should give you an angular rotation or angular acceleration. So which I times G, I sub G times alpha should be the summation of moments, okay. All right, so we can write those three equations. The first equation is in the normal direction. In the normal direction, there's only one force, okay, so that's the only ON. All right, at this particular moment, when you just cut it and you just cut the cord, the velocity, angular velocity should be 0 now, and then start to increase, okay. So at this very moment when it's just cut, omega should be 0, okay. So then ON should be 0. All right, you guys still at the horizontal position, so ON is 0. In the tangential direction though, there are two forces, okay. The weight, there's this OT. So the weight is in the positive tangential direction, OT is in the negative tangential direction. So you can write this minus OT plus the weight equals to mr alpha, okay. Mass is m, r is 0.15, and then alpha is the unknown. Okay, so we have one unknown here and then two unknowns here in this equation. All right, now you will need another equation. All right, the third one here, summation of moment should be equal to I times alpha. Okay, I about O should be equal to IG plus MR square. Okay, now let's know external moment on this rod. So then the only moment will be the torque of the weight on the rod. Okay, so it will be the mgr or rmg. Okay, r times m times g. That should equal to this together. Okay, then we can figure out about this term in the squares here, in the square parenthesis here. Okay, so I sub O, okay, because I about G halfway, midway in a rod should be equal to, again, 1 over 12 ml square. Okay, Rg is 0.15, so we can calculate that. M is 15, L is 0.9 divided by 12 plus the mass times R square. Okay, so it's 1.35 times alpha then on this right hand side. So then we can use that to solve for alpha, okay? After you do the math here, the alpha is going to be 16.4 radians, okay, per second square. And then find the, put the alpha back into equation 1, which is the second equation, okay? So then you can solve for your OT, okay? OT is going to be 110 newtons then, okay? It turns out to be that. All right. Any questions you guys might have? So if not, then I'm going to have you guys work on the attention quiz here. Okay, I have the breakout rooms are still open. You guys can join the breakout rooms, okay? So join your breakout rooms and then work on these two quizzes. All right. So you're all back. Let's take a look here. The first one says a drum of mass m is set into motion in two ways. So you can pull it directly with a force of 40 newtons. You can also put a weight of 40 newtons to do it. Okay. So let's look at the two scenarios here. So for the first one, because we'll be comparing the angular oscillation, so then we'll just be looking at the third equation for the net moment to be equal to I times the alpha. Okay. So for the third equation, scenario A, then you are going to have the moment of inertia times alpha A. Okay, that should be equal to, so the moment on the drum should be caused by this pulling force of 40 Newton. So that's the torque by this 40 Newton. Okay, so R times F. On the second scenario, now you put a weight of 40 Newtons to the drum. So then there will be a tension force of T, okay, which is not necessarily actually equal to the force F, okay? And that's because, but for the drum, it's again the I times alpha B should be equal to R times this tension force, okay? Now let's look at what would be this tension force compared to the force, pulling force F, okay? So if you just look at the weight itself, the weight should have two forces on it. There's one of the weight, okay, F, or I should put, yeah, this is the weight is the same as the F, so that's why I put F here, minus the tension T equals to the mass times acceleration, okay? Now, because this guy is not zero, M is not zero, A is not zero, so then this is greater than zero, okay? So if F minus T is greater than zero, that means F is greater than T, okay? So then if you compare this to if F is greater than T, then you realize that alpha on A scenario should be greater than alpha on the scenario B. Okay, so this would be giving you answer A in on one. Okay, so on one it's A for the answer, correct answer. On the second, B, second quiz here, 2, in case B, what's the tension in the cable, okay? Now there's options of equal to 40, less than 40, or greater than 40, okay? So again, if we look at the weight, the mass, so there's this weight of itself, then there's this tension, okay? So, and then this is M, okay? So F is equal to mg. In this case, it's equal to weight, okay? So you can see that F minus this guy is greater than 0. Okay, so that means F is greater than T, so our T is less than 40. Okay, so this is based on on 1, actually, problem 1. If you know problem 1, then you realize problem 2 should be having T less than F, which is 40. Okay, so that should be the correct answer there. All right. Any questions you guys might have before we head to the group problem solving? All right. So if not, then let's take a look on this group problem solving. So if you have this pendulum, which consists of 30 pounds of sphere and then the 10 pound of rod here, it's asking you what if you just cut chord AB, what would be the reaction at point O, okay? So, or we should say the reactions at point O. You probably will consider reactions in the tangential direction and then normal direction, okay? So the plan will be, again, draw the free body diagram and then connect the diagram and then apply the equation of motions, okay? So I'll let you guys work on this. So again, I will open up the breakout rooms. You guys can try to solve for this one. And then at the end, I will show you the solutions, okay? So let's do this again. Open all the breakout rooms again. All right, I had to force you out of the breakout room because we are at 150 now. Okay, so here's the solution I show you here. Okay, so basically you take those three equations, 1, 2, and then another one is about the net moment. Okay, that should be equal to I times alpha. Okay, so I'll post the solutions later online, but those the three equations to start with: the free body diagram, kinetic diagram, and then with those three equations, and then this is the answer at the end. Okay, so I'll post the solution online. You guys can check it online later. So, any questions you guys have at this point for today's class? All right. Otherwise, have a good weekend. I can see you guys on Monday. Bye bye.
See ya.
See ya.
Bye. Have a good weekend.
Bye.
Hi, Dr. Ho.
Bye.